Okay, welcome to one of these talks. This one is about covering spaces. I was initially going to try to prepare a talk about p-adic integers, and I didn't have time to figure out all of the details, and so I committed to giving a talk anyway, kind of stupidly. So I thought, oh, covering spaces, that's something that I can just rederive in 2 days. I didn't quite get there. So there's some details of some things that I haven't filled in because I didn't take the time to look anything up. And we're going to just go through the big ideas. Just want to talk about the big ideas of covering spaces. I'll just skip over details and refer to you to sources when it's a good idea to do so. And so before I forget, I should write down just a list of names who've all written textbooks about things that cover covering spaces. There's lots and lots of resources for you to go look. This is why it's kind of a fun exercise to do for yourself. Because, I mean, you can always look it up, but you know it's easy enough that you can just kind of figure it out if you sit down for long enough. So there's Hatcher, obviously, as always. There's his usual book, Algtop. This one's nice. You get it for free from his website. I think it's Harper and Greenberg. I think. I'm definitely going to get this wrong. They have a book on algebraic topology. Fulton has a book on algebraic topology that talks about covering spaces. J.P. May has a really nice book called A Concise Course on Algebraic Topology. He takes the perspective of groupoids, and he talks about a covering space of a groupoid, and then just says, okay, now consider the fundamental groupoid of a topological space, and he extracts everything that I'm about to say. So if you like a little bit more abstraction, you can look at the groupoid version here on algebraic topology. It's really nice. A lot of the things are basically the same. But I'll just keep it lowered down to the earth, even though we're talking about algebraic topology. Okay, so here's the resources. Go and look them up, please, because I'm going to lie to you, and I want you to actually learn this content because it's great. Okay, what's the point of covering spaces? Why do I want to give a talk on covering spaces? It's a really, really great talk to introduce students on the interplay between topology and our usual algebraic invariants, in this case, the fundamental group. So I've talked before about things like fibrations and covering or fiber bundles, and I've mentioned a lot that these things have something called the homotopy lifting property. So let's remember what that is. Right? So if you have a base space B and a total space E and a map F, and if you have some test space X and let's say a test map tau, let's think about this more organized way. So you want to say that P has a homotopy lifting property with respect to X if, so for, how do I say this? For every kind of initial bit of data, test data tau into the big space upstairs. So let's say we have some initial data tau upstairs. If we project that down to B along P, and then sort of take a homotopy of it, so this is the inclusion of 0, can we lift the homotopy downstairs to give us a homotopy upstairs that starts with tau? So what is that in words? So P has the homotopy lifting property with respect to X if for all tau maps from X into E and homotopy H downstairs, where H starts at, so Hx0 should be equal to the projection of our test map at X. So it's starting with projecting downstairs. Then there exists a homotopy lift, which is what we call it, H tilde into E. Why do we call it a lift? Because we require that if we project it as a function from X cross I to B, projecting it down should be the same as H. So like for all time t, What this is saying is our function into E lives over whatever it is at time t downstairs. So we want it to be a lift, and I think that's it. Oh, and we want it to start with tau. Yeah. So this is the homotopy lifting property. This is what we would call the homotopy lift of H with initial data tau. So here's some terminology that I'll probably use. So H tilde is the lift of H, or rather is a lift of H with initial data tau. Okay, so homotopy lifting. Sometimes you want to consider situations where your map P has the homotopy lifting property with respect to all spaces X. And this is called a Hurewicz fibration, and it gives us all this great homotopy stuff. You get long exact sequence and homotopy groups, etc. Sometimes it's enough to only assume that you have homotopy lifting property with respect to CW complexes. That already gives you a long exact sequence and homotopy groups and a Serre spectral sequence, etc., etc., etc. So fibrations and covering spaces, they have this homotopy lifting property, at least for CW complexes. What we're going to see for covering spaces, what makes their entire theory work is that when you write down your homotopy lifting property, the theorem is actually there is a unique H tilde with this initial data allowing you to lift. So with a fiber bundle, it's sort of like you have a lot of freedom to go up and down in the fiber directions. But a covering space, once we see the definition, it's going to be clear that like your fiber directions, you're sort of fixed. Everything comes in layers and sheets, and you're stuck. There's only a unique way to lift things, and this is going to really drive the entire theory. So that's the kind of motivation here. So let's get going. So let's let P from E to B be continuous in the sense of topological spaces. We're going to say definition. So a subspace, so U in B is evenly covered by P if, when you take the inverse image of U in E, it kind of just looks like a bunch of disjoint copies of U itself. So if there is a homeomorphism, I'm going to write it like this. So the inverse image of U, like I said, this is living inside of E upstairs. This projects down to U, or B if you want, but specifically projects to U. Sorry, I called it P now. Yep. So this is, P restricted to U, maps down to U. And over here, we can consider a product of U with delta, where delta is a discrete set. So in other words, if you wanted to have a topology, it's the discrete topology. And then we project down onto U. I'll just call that pi U as the projection map. So to be evenly covered requires that this is homeomorphic to this in a way that makes this triangle commute. So let's call this homeomorphism phi U, I guess. So saying that this triangle commutes means that for every point in U, anything in here that maps to U maps to something in here that also maps to U. In other words, this is a fiber preserving map. So, yeah. So to say that U is evenly covered means that the fiber over U basically just looks like a stack of pancakes. This is the technical terminology I will use. This is the word I use, is stack of pancakes. So this is like U cross delta. Right, here's your discrete set delta. These are all copies of U. This is P restricted to U. And in particular, you see that for each of these little slices, the restriction of this map to each individual slice is actually a homeomorphism. So how do I say this? Yeah, for all delta in delta, P restricted to, say, U cross delta, where we're considering U cross delta to be a subspace of E along this homeomorphism, that this should give you a homeomorphism between your individual slice and U. And this is just because it's a map over U. Okay, so this is the picture you should be thinking about for an evenly covered neighborhood. And then we say a covering, so we say that P is a covering space. Let's say, for example, this is one way of saying it, if for all B in B, there is an evenly covered neighborhood that contains B. So every single point has some neighborhood so that when you look at the inverse image in E, it just looks like a stack of pancakes. Okay, so that's our definition of a covering space. Is there anything else that I was going to say that's good to know here? Yeah, one thing you can think about this, because an evenly covered neighborhood, notice that any smaller neighborhood, I want to say this is open now. There is an evenly covered open. Yeah. So since if this is, blah, blah, blah. For any smaller subspace, you can just restrict this whole picture to that smaller subspace and see that, in fact, any smaller subspace is still evenly covered. So this condition that every element of B be contained in some evenly covered open neighborhood, this is actually telling us that there is a basis of B consisting of evenly covered neighborhoods. So you might as well just consider your basic open sets to be evenly covered. So in the same way that, like, you know, the open balls of radius 1 over n at rational numbers, that's a really, really nice basis for Rn. When you're dealing with covering spaces, you want to reach out for a nice basis. This is a good one, an evenly covered basis. Okay, that's just an aside. So let's look at examples. Are there questions that anyone wants to ask about just the way that I've given this definition? Yes. What's what? Okay. Did I write something like not very well? Okay. Okay. Okay, so here's sort of the easiest example to think of. So I'm going to take a map from the unit circle to the unit circle, considered as, you know, the unit numbers in the complex plane. I'm going to call this map eta d, where eta is going to stand for exponentiation. And we're going to take a complex number z to the power d. And we're going to let d not equal to 0 so that this function isn't constantly 1. Okay, so just let's draw a picture. Here's our circle. Here's 1. Here's our other circle. Here's also 1. So what this is going to do is subdivide our circle into like d little small segments. And if I don't draw this right, I will be embarrassed. It's close. One too many. So close. Sure. So it's going to subdivide our circle into d segments so that each of these segments wraps once all the way around the circle. Okay, so just in terms of explicit symbols, let's let zeta d be e to the 2 pi I over d. So that would be this one here. And then the pre-image of 1 is going to be all of the integer exponents of zeta d. So eta d inverse of 1, this is just the set of all oops, not xi, zeta d to the k, such that 0 less than or equal to k less than d. And then if you just keep adding more numbers, you just don't add anything else to the set. So this is a minimal index set to talk about the preimage of the number 1 under this function. By the way, we know from complex analysis that this is continuous. Or rather, because this is just a polynomial. Polynomials are continuous. So this is a continuous function. There's nothing controversial about that. So let's see that let's see that 1 is evenly covered. This is what I'm doing. Let's show 1 is evenly covered. So we want to find an open neighborhood of 1 so that its inverse image under this map is a disjoint union of open neighborhoods, so that if you restrict this map to each of those little slices, you get a homeomorphism. And so I think I'll just write them down and then we can see. So for starters, let's let U be equal to, I'll leave myself some room. Let's let U equal to the set of all e to the it, such that t is in the interval from minus pi to pi. And let's take the notation u over d to be the set of all e to the it, such that t is in negative pi over d to pi over d. Okay, so this is u, and then u over d is this one here. It's d times d is small, right? Because you can tell if you go halfway around this way, right, each of these segments is supposed to wrap 1 times all the way around. So going halfway around this way only gets us halfway to the next point. Now the idea is, okay, well, we have this one little open neighborhood. What if we just translate this neighborhood around to each of these points? And why don't I use chalk that has colors on it, so it's like easy to see the difference between all of these things. So the translates are going to be, say, in blue, assuming that the blue looks any different from white. So I'm just drawing all of these little translates of our UD around the circle. So now, right, if you're following around this way downstairs and kind of following along upstairs at the same time, when you pass over this point where your angle is pi, you jump into this other neighborhood. And you follow through this other neighborhood until you get to here and then jump into the other neighborhood. It's very interesting. But anyway, we can use these powers of zeta to just translate this around. So let's let uk be defined as zeta d to the k, translating u over d. This is a complex number, and this is a set of complex numbers, so you're just rotating it by 2 pi over d. And then you can check that eta d inverse of our neighborhood u is actually the disjoint union over k of uk, and eta d of uk is mapped homeomorphically onto u. So therefore we have evenly covered. So therefore 1 is evenly covered at least. And since 1 is evenly covered, we can just take this entire picture and rotate it to whatever angle we want to get even covered over that spot as well. So this is a covering space. Cool. First example, I think that's the only one I'm actually, well, I might work out the other one as well in excruciating detail, but I wanted to have some actual numbers and stuff written on the board, something real, even though it's just complex analysis. Okay, are there questions on that example? Because it's kind of one of the important ones. Good. Here's the next example, which is the more important one. But we don't know why yet. We'll see. Why do I say this? Well, there's no way of leading into it. Let's take the exponential function from r to s1. What does this do? This takes t to e to the 2 pi I t. Do I want 2 pi I? No, I don't. That's not what I did in my notes, and so I'm not going to change on the fly. I'll just take it. I think there's a physics convention that includes the 2 pi, and the math convention does not. And the math people are just grown up enough to not need to have a 2 pi hanging around in their function all the time. Anyway, that's a mean thing to say, so I'll move on. Okay, exponential function, right? What does this do? So we have the real line, and we have a circle. Here is our number 1. Here is our number 0 on the real line. So when we exponentiate down, we go and go and go and go and go until we hit 2 pi, and then we get back to 0. And then we get back to 0 when we're at 4 pi. And we're at 0 when we get to 2 pi. Rather at 1, I mean. 4 pi, et cetera, et cetera, et cetera. So we can play the same game, and we can define our u in the same way to be the open interval between minus pi and pi. And then we go and we translate our open interval around to get our other open sets, giving us our evenly covered blah-de-blah. So let me just write down some words and formulas in order to actually say that I did this example. Okay. So we are going to say, let's look in particular, if we pick an arbitrary e to the I theta on the circle, for example, 1, if we let theta equal to 0, this is going to be the set of all real numbers such that t is, how do I write this? Sure, start like this. By definition, this is what we get. And then because of what we know about trigonometry, we know that this is the set of all t, so that, why did I wrote a very small, okay, t equals theta plus 2 pi times some integer for k and k and z. Right. So for 1, we know it's 0, 2 pi, 4 pi, minus 2 pi. Anything else is just rotated by a little bit. And so we can let our uk defined to be equal to 2 pi k minus pi, right? Just translate everything by 2 pi k, and then 2 pi k plus pi. And then this is our evenly covered open neighborhood of u, where I had u is here, and here's my uk's. So x inverse u is equal to the disjoint union of k and z of our uk's. So evenly covered. And we use what we know about the exponential function to see that it actually is a homeomorphism when you restrict to each of these blue things. All right. Just wanted people to have some hands-on examples of covering spaces. Here's a note that you can prove immediately in your head. If M is a smooth manifold, and if you have a covering space over M, then that covering space is also a smooth manifold. Or it doesn't even have to be a smooth manifold, it's just locally Euclidean, but also works for smooth manifolds. It's just because, like, if my thing here is a local Euclidean thing, then each of these slices is also a local Euclidean thing. And so since everything up here lives above something down here, you can always find an evenly covered neighborhood down here. Restrict to an even smaller neighborhood that's a disk. And then you look at this family of disks, and one of them contains that thing. So you have a basis of disks in your topology. Okay. Here's an example that's not a manifold. Take 2 circles and wedge them together. Okay, so I'm just going to draw some examples of covering spaces. Here's one such thing. So we have these covering spaces of circles. What we could do is treat each of these as a separate circle and then take some covering space over each of those factors, right? Suppose like maybe we have like a 5-fold covering space here. And then over here, maybe we only have like a 3-fold covering space, right? You just wedge. If you have a covering space over one of the things and over the other thing, you can just wedge them together to get a new covering space. What else can you do? You can do funky stuff like this. Right? So you basically can take each of these and like fold it like that, and fold this one, and then fold, or like take both of these and fold them together in half. So yeah, if you use this point as a pivot point and like a line of reflection and then fold them in half, then you can see that in fact, oh no, that point wouldn't be evenly covered. Ooh, or would it not? Ooh, I'm not sure about this one actually. Exercise, try to make this example work. So here's a question mark. Does this example actually work, or did I invent a lie? Here's an example which does work. Take the real line, and that at every integer, add a circle. Or at every 2 pi or whatever, add a circle. So that amounts to taking one of these circles, unwinding it, like we had over here with the exponential function, but then every time you come back to the origin, well, there's another copy of the circle. Okay, well, if you did that, what happens if you take each of these circles and then try to unwind all of those? Well, if you try to unwind this circle, right, what you're going to end up getting is a line like this, circle, 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 but now at every integer we get another line that's like circle, 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 right? So the more you unwind, the more kind of circles you encounter, and it becomes this sort of nightmare mess. So that's something for you to think about when you get bored for the rest of the talk. So there's a lot of really weird things happening in this theory of covering spaces, but it's not that weird because it always like at least has the local behavior of whatever you started with. Examples, done. Okay, we can move on to section 1. So this was lifting lemmas. Okay, so the first lifting lemma is actually true for a much more broad class of spaces, but my proof that I came up with only works for cubes, so I'm going to defer you to Hatcher for the actual proof. Okay, I'm going to call this lifting lemma 1. Okay, so if P from E to B is a covering space, and if we have X, say if we have initial data for a lifting problem, X to tau, H from this to B is a lifting problem. So when I say that this is a lifting problem encoded in this statement, I'm meaning that like this homotopy starts at P of tau. So that's contained in this statement that this is a lifting problem. Then there is a unique lift, H tilde, of H. Right, so for all of our other fibrations, literally by definition, a fibration is something that you assume everything has a homotopy lift. In contrast to a general fibration, for a covering space, there's always a unique lift. So like I said, my proof, I came up with one for cubes. That's enough to ensure that this is true for all CW complexes, which is already pretty good. But the fact that it's true for all spaces is amazing, kind of. Okay, do I want to actually lug through this proof? I'll give a sketch. Yeah, I think even if I rush through all the material today, I probably won't have enough time anyway, so I might as well just like sketch things. and have some material for next time anyway. Okay, so proof sketch. This is pretty cool. This is basically based on a. Okay. Sure. For cubes only. So let's let y equal to the n cube. Then in particular, your homotopy is going to be defined on a cube which has dimension 1 larger. Okay? Right. Cover B by evenly covered sets. And let's call this collection of open sets script U. And take H inverse of U, collection of open sets covering the cube. Let's call this something. Let's call this mathcal H. Okay, it's a collection of open sets covering the cube. By compactness, we use the Lebesgue number theorem, like that one, Lebesgue number theorem. To get, so there exists a delta bigger than 0 such that for all k subset of the cube with the diameter of k less than delta, so there is a delta so that for every sufficiently small set, diameter delta, there's some open set U in this collection with k contained entirely in U. So the point of this is that now we can take our cube and break it down into super, super small subcubes so that for every single one of our subcubes, its image in B lies inside an evenly covered neighborhood. Then we can use the evenly covered neighborhoods, which have local homeomorphisms, to lift up into the total space. And so the concern is to do this in an organized enough way to make sure that like everything is well defined. Okay, so maybe I draw a picture. Here's a cube. The whole point of this is pictures, right? So maybe we choose an L or an N and let L be 1 over N. And suppose we choose it so small so that we get all of these tiny little cubes. I'm sure I didn't actually draw them as cubes or whatever. It's fine. I think this is like a 5 by 6 cube or something. Oh, that's horrible. That's a cube. Believe me, this is a cube. So I'm going to consider this cube as like IN cross I. So at this end, there's sort of like this thickened n-dimensional slice. And then going this way is like a one-dimensional extension with parameter t. Okay, and then we're mapping this big cube into B, and this is covered with a bunch of evenly covered subsets. Right, and so the idea is that for a little cube, one of our little cubes, this goes entirely inside one of our evenly covered sets. And any one of our cubes lands inside one of these evenly covered sets. So here's the lemma that makes it work. It's pretty easy. Let C be a cube. So let C, be a cube in IN. So I'm just taking some subset so that the image is contained entirely inside this thing. So if our lift is already defined on a connected subset of C, then there is a unique extension of H across this cube C. Okay, so maybe you can believe intuitively why might this be true, right? So if we already have, say, like on the front face, we already have an extension, right? So then this open neighborhood here that contains our cube, we get this evenly covered stack of pancakes upstairs. If we already have a function defined on a connected subset, so it's already lifting into here, by connectivity, it has to appear in exactly one slice. There is a well-defined slice that contains our already defined function on this face. And so we can just say, all right, well, let's take this projection map restricted to this slice. We know that's a homeomorphism, and then just compose to get a lift on the rest. That's the idea. It's a really simple idea. This is why we use Lebesgue number to get a small enough covering, is so that on each of these atomic pieces, we're basically allowed to lift for free as long as we've already chosen which slice we're going to lift through. So then the game comes down to, okay, we need a way of, one by one extending this function h cross or h tilde on these cubes so that one of the faces is always defined, but you can sort of reason how to do that. We already have it defined on the entire left side, so you can just come up with like a recursive way of just doing one slice at a time. That part's not complicated, it's only just annoying to write down. The important part is that the even coveredness, the fact that we get this disjoint union of slices, is what lets us get the uniqueness of the homotopy lifting. So that's just a proof sketch. Hatcher has a slightly more sophisticated one that works for all spaces. I just didn't have enough time to parse it before coming today. Okay, yeah, that's what I wanted to say about that. So questions about that would be good to ask now. Yes? The Lebesgue number theorem says exactly what it does here. So if you have a compact set, then if you have an open cover of that compact set, so compactness means you can find a finite subcover, okay. But the Lebesgue number theorem, if you're in a metric space, it says no matter what open cover you have, there's a delta small enough, a really tiny small delta, so that every open set of diameter bounded by delta sits inside one of your open sets. So that's exactly kind of, so this right here, this is just me deducing like literally from the Lebesgue number theorem. This is kind of like literally what it says. Yeah. Yeah. So there's some smallness that fits inside of every element of your cover. Or rather, you can think about it in terms of like the elements of your cover have a minimal amount of, there's like a maximal amount of minimal overlap or something like that. So there will be sets that don't intersect that much, but like you can always find sets that will intersect enough. That's not a good way of saying it. Okay. Powerful thing, corollary. Let's just take the easiest possible case where our n is equal to 0. So let gamma be a path in B. And choose an element E in the inverse image of the start of gamma. So yeah, why don't I draw? Here's an interval. Here's gamma. Or rather, this is how it sort of write. Here's gamma 0. Goes somewhere else. Here's gamma 1. And each of these have their stacks of pancakes. And we've chosen an element over gamma 0. So that's the same as choosing an initial lift of our n cube, where our n cube is now a 0 cube. Okay, so there's gamma. Then there's a unique gamma tilde. Which lifts gamma and so that gamma tilde starts at E. Okay, so choosing E says, okay, there's only one way right? Basically, you just follow through your evenly covered neighborhoods. There's only one way to get a path upstairs that covers this path downstairs once you've chosen where it starts. So this is kind of like your linear ODE result. If you have a boundary condition, you get a unique solution. It's kind of wild, but this is the case. And I think those two facts are probably related. I'm not sure. I know that the complex logarithm function is equivalent to the homotopy lifting property for the exponential map. So that's where that comes from. It's topology. Okay, so this is unbelievably powerful. I'm going to take a drink right now because this is like the most powerful result, even though it seems like a totally ineffectual thing. This fact is going to appear in like every proof from here on out. Let me just make sure I actually wrote it down right. Oh, this should be P. Seems okay. Okay. What this means is a path induces a function from the fiber over gamma of 0 to the fiber over gamma of 1. And I'm going to call this function, get ready for this, L sub gamma. This is, for whatever reason, I called them L's because it's funny. Okay, so this is my function L sub gamma. You get a function from a path. And the lemma, suppose you have two paths which are homotopic relative endpoints. So what do I mean by homotopic relative endpoints? I mean that like your homotopy is like a path of paths. Each of these paths, they all start and end at the same place. So like you imagine, like here's your starting point, here's your ending point. Maybe this is one of our things. Another path that's homotopic relative endpoints, right? We might just have like a continuous family of paths that interpolate between these two. They all are forced to start and end at the same place. All right, so in particular, they all induce functions from here, from this fiber to this fiber. Then they are the same function. L gamma equals L gamma prime. So this is where homotopy invariance, just like, I don't know what language I should use here, but it puts itself in the picture, whether anyone wants it to be there or not. Here it is. It's just, this is the spot right here. You get functions. Any path gives you a function between these two fibers. And if they're homotopic relative endpoints, it's the same function. It's the same function. So let's look at a proof. Let's see if I can figure out what I wrote here. What's the idea for this one? So let's start with one of these things. So take a homotopy relative endpoints. That's going to be defined on a square into B with the following properties. So first of all, it has to be gamma at the start, and it has to be gamma prime at the end. And to say that it's relative endpoints means precisely this. Gamma 0 of S, so this is for all t. Gamma 0 of S has to be gamma 0, which ultimately then has to be gamma prime 0. And gamma 1 of S has to be gamma of 1, and ultimately also gamma prime of 1. And this is for all S. So this is what rel endpoint means. Okay. Now, for whatever reason, I've chosen to draw a covering space like this. It seemed like a really cool idea at a time, and I think I still agree. Okay, so let's say down here we have an E. So like this is gamma of 0. So let's let E be in, what, P inverse of gamma 0. And we want to evaluate the functions on E to see if it agrees or not. Okay. Let gamma tilde be the lift of gamma starting with E. Okay, so let's say, let's actually draw our thing downstairs. Maybe here's our 2 points. This one's gamma, this one's gamma prime. And so here we go up, dot, 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 dot. Maybe we're over here. This is gamma tilde of E. And then, aha. And now use this as initial lifting data to lift H itself, okay? So we have H is a homotopy down here between these two paths. So what we can do is first just choose one E that lives down here, okay? But now by uniqueness of homotopy lifts, we can start with gamma and lift whatever that path is downstairs to something up here. And I'll try to actually draw it so that it lives over the thing that I drew downstairs. Okay, but now it's like we have, for this function up here, for this homotopy, we have a choice of function upstairs for our value s equals 0. It's our gamma tilde. So now we can lift the rest of the homotopy to an h tilde. And how do I make this make sense? Okay, I'll just write down what I have on this page, and then it should make sense because it made sense to me at the time. Just bear with me. I completely forgot about this proof. Okay, so since what? P, so if we take h tilde 0s, right, by definition of a lift, this is h, and this is fixed, right? So this is equal to gamma tilde 0 for all s. Sorry, no, gamma tilde, gamma 0 for all s. And since P inverse of gamma 0 is discrete, finally discreteness is important. Well, again, discreteness is important. So the idea is that, right, so you have this homotopy downstairs, which is taking this endpoint and leaving it fixed. So the only thing that a lift upstairs could do is move it up and down in the fiber, but there is no moving up and down in the fiber. Since the fiber is the discrete topology, you're stuck here for the duration of your entire h tilde. So this means that h tilde 0s is actually equal to gamma tilde of 0 for all s. Well, actually, I should have meant this is over here. H tilde is fixing this point. This argument shows that h tilde fixes this point, and then a similar argument. H tilde also fixes 1. And it's going to have to agree with whatever our initial lift was. Somewhere I wrote it gamma tilde. This is for all s. So in particular, you consider the path h tilde t of 1 lifts gamma prime, and its value at 1 is equal to gamma tilde 1. So gamma tilde 1, this, remember, means this is L gamma of E. And this gamma tilde 1 then also has to be, okay, let me phrase this better. What is wrong with me? Okay, what have I written on my page? Stop trying to ad lib. Okay, here's the point, is that the other end of this h tilde is a path that starts here and goes here. This is the point, is whatever our lift of this h is downstairs, the two endpoints are fixed, right? So since our function was defined by taking this path and lifting it, so now I can draw in the other path. Sure, I'll draw in the other path. And so because our endpoints had to be fixed the whole time, our homotopy upstairs also has to fix the endpoints for all time. And so our L function, which is defined by lifting the path and then taking the other end, these two L functions have to give us the same thing. So this is the moral reasoning here. So this is our gamma tilde of 1, but this whole argument shows that that's the same as the gamma prime tilde of 1, which is what we called our lambda, our L gamma prime of E. There it is. Okay, yeah, boom. So this one was a little tricky. This was not just a formal application of something, because we had to really invoke the fact that the fiber is discrete in order to verify that our homotopy that we lift upstairs keeps the endpoints fixed upstairs too. Yeah, that's how okay, sorry. I got really excited about that argument. I think it's so cool. And if you sit down and figure it out by yourself, you will too. So all of this is an exercise for you to reproduce on your own, in your own way, as long as you don't do it wrong. That's the only constraint. You just aren't allowed to do it wrong. You can find your own way as long as it's not incorrect. Okay. Wow. Sure. Okay. So recap, what does the lemma say? Given any path from 2 points in B, you get a function between the fibers. If you have a homotopy relative endpoints between your paths, you get the same function. Now we'll see that these functions are all bijections. Every lambda gamma is a bijection. All right. And what is the idea? The idea is that the inverse should be given by just doing lambda back or doing gamma backwards. So I think I'll actually skip the proof and let you guys do it. So the idea is that lambda gamma inverse is really just lambda of gamma bar, where gamma bar t is defined by just doing gamma in the reverse order. Yeah, so I've got a few lines of very funny, oh, so I don't get to force the funny notation on you, but it's so funny. Oh my God, no, I'm gonna do it. Sorry, guys. If you're gonna make me give this talk, then I'm gonna have to give this argument. Okay. You have a question? Or fair enough. Fair enough. Okay. Unless I did it wrong, in which case I'm just gonna be very embarrassed. Okay. Okay. So here's the idea. So now let's say for each E in the fiber over our starting point, let's lift gamma to gamma tilde sub E. So E is the initial point of this lift. So for every E, we have like a family of parallel lifts. So by definition, on my page, I'm saying that L sub gamma of E is equal to gamma tilde E of 1. This is the definition of our gamma and our L. So if, so now, okay, now lift gamma bar to, so this is a path downstairs. We're going to choose an initial point upstairs to use as our subset, and we're going to use E prime. Yeah, okay. I'll write it like this, to gamma bar tilde sub E prime, where E prime is just the other end of our gamma E. Okay? So by uniqueness, so gamma bar tilde E prime, this is a path upstairs that starts at one end of this and then comes back, by uniqueness, it has to be this function going the other way. So this must be, what am I saying? The lift, aha, it must give you the lift gamma E tilde, but going backwards. So now the bar is on top of the tilde. This is good. So now we just do a computation. Okay, so L gamma bar circle L gamma of E. This is equal to L gamma bar of E prime by definition. This is just at the other end. Now this is equal to, what did we say? L bar tilde E prime of 1. And this is equal to, because we said it's the same as this, gamma tilde bar E1. And this is equal to gamma tilde E of 0. And this is equal to E. So therefore, this is the identity on the fiber over here. And similarly, you can draw the other way around. This is the identity over the fiber at the other end. Yeah. So if you can just parse what the symbols mean, then it's a perfectly sensible argument. That really just amounts to the fact that, yeah, the inverse is given by just taking the path backwards. There's probably a better proof that you can do as well, but oh, I see what I did. Yeah. I remember now. So I established this first before I did this, and then I realized that you don't actually need this to get that they're all bijections. Aha, yeah. So this argument shows that they're bijections without using homotopy independence. In fact, it's way easier to use homotopy independence, specifically because you can just go like this. This is just a constant, right? So this is constantly, yeah, if I do gamma and then gamma bar, this is constantly gamma 0, homotopic to it. And then if you do gamma, yeah, gamma bar concatenated with gamma, this is constantly gamma 1. So, and the constant function gives you the identity map over the fiber. So you can use homotopy invariance to make this way easier. I think I just figured this out after the fact, and I meant to give this before the homotopy invariance argument. So now everyone's really confused. But the point is, every path gives you a bijection between the two fibers over the two endpoints, and if you change the path by a homotopy rel endpoints, it gives you the same bijection. Okay, that's what we've established. In particular, if you have a loop, then this acts on the fiber. So corollary. So pi 1 b acts on P inverse of B. So every loop just gives you an automorphism of the fiber by this uniqueness bijection stuff. Yeah, every loop gives you an automorphism, and because homotopy rel endpoints preserves the automorphism, this descends to an action on the fundamental group itself, not just on like the loop space giving you a monoid action or whatever. Okay, proposition. Yeah, I'm definitely doing this in the wrong order, but that's okay. So if E, the covering space, is simply connected so then this action is free and transitive. Meaning that if you choose a base point in the fiber, the action establishes you a bijection between the fiber and the fundamental group itself. So if you have any simply connected covering space, the fiber is in bijection with the fundamental group. There's an extremely strong constraint that places, there aren't very many simply connected covering spaces. I'll just say it like that. Okay, how do we see this? So So let F0 be the fiber over the base point. Save us some writing. Since pi 0 e is 0, so simply connected means path connected and pi 1 vanishes. So pi 0 of e is also trivial. Choose a path in E in the total space from this point to some other point E prime, where these are both in the fiber. So choose a loop taking from one element to another in the fiber. So therefore, if you project this downstairs, this is a loop in B. And by uniqueness, all of this stuff adds up to tell you that your lambda gamma of E is equal to E, lambda of P gamma, yeah. L of P, the projection downstairs. Draw a picture. Yeah. So upstairs, here's E, over the same fiber, remember, here's E prime, downstairs here's B naught, and we choose a gamma. There's a gamma, maybe a different color from the rest of the thing. Here's my gamma upstairs, and then we project it downstairs, and we get P circle gamma. And then write what the definition of this action means. I've chosen my gamma to go the wrong way. I'm sorry. Fix that. Okay. Right, the L was defined. This action is defined through these L's. And it was defined by, okay, well, what do we do to E? We take our loop downstairs. We act on it like this. And wherever we end up, that's the answer. And so we start with a loop, with a path upstairs. We already started with a path upstairs. Project it to get a loop downstairs because the two endpoints are in the same fiber, and then use unique homotopy lifting of this loop to say that, okay, well, whatever lift you have that starts at E, it had to be the path that we already started with, right? And so the way that this loop downstairs acts on E is by sending it to E prime. But we just chose E and E prime arbitrary. Arbitrary. Right, so no matter what E and E prime we find, we can always find a loop downstairs so that it acts on E to give us E prime. So therefore, this action is transitive. That's what transitive means. Okay, and now we need to see that it's a free action. What does free mean? Free means that if you have a loop downstairs that fixes a point upstairs, then it has to be the trivial element. Yes. So let's see what that means for us and our very strange action by loops and homotopy liftings. So suppose gamma is some loop in B, based at B naught, so that, well, let's say, and let's pick an E in our fiber over B naught, so that our L function on E is actually just E. Okay, so that means if we lift gamma to, say, gamma tilde using E as our initial data, this means that gamma tilde starts and ends at E. Okay? Right? But we did assume that E was a simply connected space. So gamma tilde is null homotopic. Via, say, H tilde in a way that fixes E. So therefore, P of H tilde is a null homotopy of gamma itself. Or in other words, that gamma had to be 0, or I'll write it as 1 because it's a multiplicative group in this thing. So therefore, this is a free action. So that's interesting. So any covering space, which is simply connected, is actually a principal pi1b bundle. That is nice. It's very nice. That's correct. Yeah, you noticed that I was about to say something about principal bundle. Yep. Good. Good.
I have a side question.
Yeah.
Can you remind me how to write pi1 of some pointed topological space as a loop space with other stuff?
So by definition, right, pi1 of your base space, this is just given by homotopy classes of loops, and you define like the concatenation of them by choosing one representative here, choose one representative here, and take the homotopy class of the representatives. And this turns out to be an associative operation with unit and inverses because you've defined it on homotopy classes themselves. But what you can do is just not take homotopy classes yet, and you get a loop concatenation which is not associative, it doesn't have units, and it doesn't have inverses, but it still has all of those things up to homotopy. There's some homotopy between this one composition and that composition, so that when you drop down to homotopy classes, it becomes a group. So pi1 of your space, pi1 of B relative B, this is isomorphic to just taking the based loop space of B. So this is just loops with their concatenations as like a topological space, and then taking the path components of that. Yeah. So you often see this operation defined on homotopy classes directly, and then they just verify that it's like well defined. But you can also just define this operation on this space of loops, but it's just not a group.
Until you take pi0.
Yeah, until you take pi0. Yeah.
We can do this for the higher groups as well.
Yeah. You can just keep doing that. So like pi n of b, b0 is loops n. Yeah. I mean, and you can do it like whatever. You can stop at any point in the middle if you already have like a convenient description of that. Yeah. Okay. Okay, so now is like the most amazing thing that you're probably going to see today, maybe. So I proved this in a special case, and then I looked at a bunch of stuff in Hatcher, and I realized my argument almost works verbatim for this more general case. So I'm going to have to remember what the more general case is off the top of my head. Okay, so suppose we have a covering space. And we have f is a continuous function to B. And let's just suppose that everything's pointed. Let's keep track of the base points. Here, base points, base points. So the E naught lives over B naught, Y naught not to B. Okay. What we want is a lift. We start with some arbitrary map into B. And we ask, what do we have to do to make sure that this lifts into E? Suppose that you start with a continuous lift. Suppose we had a continuous lift. This necessarily means that if we look at our homotopy functors, pi1 of f factors through pi1 of E, right? So if we had a lift, we could take this map on homotopy groups and factor it through this map on homotopy groups, then this one. In particular, this would mean that the image of f on homotopy groups would have to be a subset of the image of P on homotopy groups. Just by functoriality, that would have to be the case. And it turns out that that is sufficient as well. If this is true, and Let's see, do I need something to be connected? This is true, and, because we've already chosen an E0. Okay, if this is true, then there exists a unique pointed lift of y. I think y should be path connected. Otherwise, this won't be unique. Okay. So all you need is this really strange fundamental group assumption, and then you automatically get exactly one lift. One lift automatically. I think this is the weirdest thing in the universe. But this is why covering spaces work. It's this lifting lemma. It's that L, the uniqueness of L functions or whatever. It all builds up into this big, great story. So let's see if I can communicate this lifting stuff. Okay. I have notes, and I'm pretty sure I know how this works. I just have to do it. Okay. Let's see. Okay. So suppose y is in y, and we want to define, what do we want the name of our function? Let's call it f. F tilde of f. Okay, so suppose there's a y and y, and we want to define f tilde of y. So y path connected. This means we can choose a gamma at least. Choose gamma from y0 to y. And then we can look at f of gamma as a path in B. And where does it go? It starts from B naught to f of y. Yeah? And now we want to use this base point as initial data to lift f of gamma to, say, gamma tilde. And then we want to define f tilde of y should be something like gamma tilde of 1. So maybe I draw a picture so this doesn't look so bonkers. Here's my y, which is a little bit strange. Here's my base space B. Here's my nice little base point B naught. Here's my nice base point y naught. We traverse the entire world to reach y. This traverses B. We end up at f of y. Each of these have openly covered neighborhoods that might not have anything to do with each other. We have a chosen base point upstairs. So this was f of gamma. And we lift uniquely to some gamma tilde. And we want to say that this should be f tilde of y. And it's sort of like, that's sort of a bizarre thing to do. It's the only thing we could have done. It's such a strange thing to do. Is it even well defined? What if we'd chosen a different gamma prime? If we'd chosen a different gamma prime and we get a different thing down here, we might get a different, so let's go like this. Here's our f of gamma prime. And it's possible we might go like this, and then maybe our lift of our f gamma prime diverges from our gamma tilde, and we end up at a different spot. Can that possibly happen? This is the question we need to address. This is the subtlety of this argument, is not even the continuous part. forgot to mention this is a continuous lift, right? So the subtlety to address in this construction is how do you even know that it's well defined? And just so that I'm not like trying to say too much about a kind of confusing thing, I'm just going to point out the following. If we have these two loops, if we have these two different paths in B, right, this forms a loop at B naught. You can take F circle gamma and then F circle gamma prime back, the barred version, to get a loop at B naught. Because the image of F is contained in the image of P, this loop has to come from a loop upstairs. That's exactly what that means. But if it's a loop upstairs, it can't have these disconnected points here. So maybe I want to write that in words. So if we chose a different gamma prime from y naught to y, could we have had like what, gamma prime f circle gamma prime tilde of 1 not being the same thing as f circle tilde blah de blah de blah of 1? Could we have had this? And the point is no. The reason being that, right, f circle gamma loop concatenation or path concatenation with f circle gamma prime bar is a loop at B naught, so is in the image of a loop from P. I guess you have to be careful because it's like up to homotopy, right? You don't know that this is precisely equal to the image of some loop. You only know that it's homotopic to the image of some loop. I'm just going to wave my hands and say that's okay. Is in the image of a loop from P. So by uniqueness of lifts, the ends of f tilde gamma 1 prime and f tilde gamma blah have to agree. So this is a really sketchy way of saying it, but this is the idea. Yeah. It's precisely this extremely weird assumption which allows us to say that these 2 points are the same. And it's by uniqueness of lifts, it's uniqueness of homotopy lifts ultimately that's telling us this. But this is the really important part. Somehow that the image of the fundamental groups controls our ability to construct lifts into the total space of a covering space. Okay. I think I can almost say something good about that. Okay. Yeah, and so in particular, we had this free transitive act, or we had this action. So corollary. So E over B covering space. So then, right, definition. Okay, so I haven't actually talked about a morphism of covering spaces yet. So far, I've just talked about all of these kind of technical lifting stuff. So so let's say a morphism or a covering space map. Good covered in chalk here. Space map, writing too furiously. Okay, is a homeomorphism. No, just a continuous function. Is a continuous function over B, by which I mean in the over category. So we have a projection for E, we have a projection for F, and we're asking for not a homeomorphism, just a continuous function from E to F that's fiber preserving. This is going to be our morphism of covering spaces. So an automorphism or an isomorphism is just a homeomorphism. Or it is a morphism which is a homeomorphism over B. I'll say it like this. And then here's a little weird name. So an automorphism is sometimes called a deck transformation. And I think the motivation for this idea is that you think of the covering space, at least locally, looks like a deck of cards. And your automorphism of a covering space is sort of you're shuffling your deck. So we have this action of the fundamental group on any fiber of a covering space. Okay, but what does this say? Suppose this y and f are actually E and P themselves, and you're looking for a map from E to E. So what do you need to construct a map from E to E? Hold on, this looks too good. So this would only give us the identity if we tried to do it like that. What am I trying to say? Aha. Suppose this was E, but it had a different base point. Suppose this was E, but with a different base point. And suppose you choose a gamma in your fundamental group here, so that this base point is the action of gamma on this base point. Then, so this action of gamma is going to permute the elements of the fiber, sure, but this proposition tells us we get an entire function from here to here. And since gamma is invertible as a path, this function is actually also invertible as a morphism of bundles or as covering spaces. So our fundamental group actually acts on a covering space by deck transformations. Right, so we initially only had an action on the fiber, but this very amazing, very amazing constructing function proposition actually lets us extend that to the entire space. Okay, so here's the proof, like I just said verbally. So let gamma be in the fundamental group and apply proposition to, we have E, here's E with the base point gamma acting on E0, mapping down to B0, and then the map that we're trying to lift sends E0 to B0. So this is P. This is the same function because gamma, E0, and E0 lift in the same thing. So this proposition assures us that there is an isomorphism of bundles, mapping from one to the other. That's crazy, right? So now we're just starting to kind of, out of nowhere, out of complete magic, we're just like, through sorcery, we're producing actions on the entire total space of this bundle just by knowing that loops lift uniquely. Okay, very bonkers. Okay, yeah, so I guess I'll just keep following my notes. Let's see, we started about an hour and a half ago. Yeah, okay, good. Should I try to aim? I have 30 minutes left? Okay, well, if I'm just hand waving my way through. Okay, no, I'll focus on this one because it's pretty good. Yeah. Okay. So, that's good. So here's a great theorem. If E, the total space, is simply connected, Then, oh, this is funny. Yeah, while I was doing all of this development, I keep coming up with theorems that are like, if we choose E, then we get a function, blah, de, blah, de, blah. And then like Hatcher just phrases it as, oh, well, why don't you just do pointed spaces to begin with? And there's no choice. You've already got one. Okay, but anyway, I'll mix them like this. So choosing E and E gives an isomorphism between the pi 1 of B based at the point under E with the notation that I haven't introduced, the set of all deck transformations of E. So this is the set of all bundle automorphisms, or all covering space automorphisms of E. If E is simply connected, then each and every one of those is given by acting by some loop. And this is like an injective thing. So let's see if I haven't screwed something up somewhere. I wonder if B has to be yeah, maybe E should be path connected. B should be path connected. Because because otherwise you'll have other components of B that act on the part of E over stuff that has nothing to do with the space point. So let's suppose that B is just path connected. Or you can suppose that this is the part of E that lives over the path component of this point. So we'll assume that B is path connected. Okay, so we have, all right. So we have an association, basically going from pi 1 of B with this base point, to the deck transformations given by the above corollary. So, and I'm going to call that acting based on our choice of point E. We still have to choose an E, right? If we had a based space, we wouldn't be choosing an E. It would rely only on this E. But since we're not fixing something, we have to fix something. So here we go from above corollary. Corollary. Okay. So first, why is this injective, and then why is it surjective? And of course, it's well defined because we have that homotopy invariance. All of these functions are really based on these L gammas, which were all homotopy invariant. So this is totally a well-defined function. So if, let's suppose that we have a loop that acts by the identity deck transformation, then in particular it fixes the fiber over the base point. And we've seen that since it's a free action on the fiber, right, you can check over the fiber. This means that it has to be null homotopic. It has to be trivial in the fundamental group. Because we know what the action is on the fiber. We know that it's free and transitive when he's simply connected. And so we could just check in one fiber because the rest of the transformation like uniquely extends the action on this fiber. It's so bonkers. So therefore, this is injective. Now, why is it surjective? So let phi be some covering space automorphism. Choose a path. Gamma from E to, what am I saying? Phi E, of course. What else? So the idea is like, okay, upstairs, maybe we have something like this. Maybe here's our E, and we have some shuffling thing that takes E down here to phi E, right? Well, we can just always take a path because E is simply connected. It's in particular path connected. Project that down to a loop in B, right? Now this loop, by definition, acts in such a way that it sends E to phi E. But then by the uniqueness of the thing that I just erased, that means they have to be the same function. This is something maybe I should have spelled out explicitly as a corollary. That thing that I just wrote down and erased says that if you have two morphisms of covering spaces that agree on a single point, then as long as everything is path connected, those two morphisms are the same morphism. That follows from that thing that I just erased. And so action by gamma sends E to phi E. And so since they're both bundle automorphisms or covering space automorphisms, they have to be the same. Like what the hell? So therefore, this path is a loop at PB, which means that P circle gamma, the loop acts on E to give, with the definition of this one, acts on E to give phi of E. Well, this means that the action by this, right, is equal to phi by uniqueness, by the uniqueness clause of that proposition that I just erased. So it's surjective as well. And my proof continues, which is making me wonder what is on the rest of this page that I need to actually verify to be done the proof. Oh yeah, if phi and phi 2 are morphisms where E is path connected, then yeah, okay, I'll just write that down because it's important enough to have written down. I said it verbally, but I did specifically use it in the proof and I forgot to include it earlier, so I'm going to write it down right now. And the proof is like an exercise. It's the same uniqueness stuff that we keep doing over and over and over. It's a good exercise in sorting out whether you really understand it or it just sounds cool. So this is retroactive lemma. This is like I did technically use it to do this, and it's good to know. Where E is path connected. So it doesn't even have to be totally simply connected, just needs to have pi 0 vanishes. Then if phi 1 and phi 2 agree at any point, then they have to agree at all points. Very amazing. Very amazing. So this and the other, yeah. I keep pointing at every result and being like, this is the reason why it's so good. And it's every single result, one after another. Okay, well, okay, so let's apply this. Let's compute a fundamental group of something. Let's compute a fundamental group. I think I'll go back to here because otherwise I'm just going to start at the end and come back here anyway. Okay. What's your favorite, I'll ask the audience, what's your favorite simply connected covering space? Or at least where the base space isn't contractible. Does it help you to know, what did you say, S2? The exact one?
Base space being contractible S2, but simply
You want a simply connected covering space over S2, or you want that to be the total space?
over S2.
What's interesting is that there are no non-trivial ones. The only simply connected covering space over S2 is S2 itself.
You said one trivial one, or is it non-trivial one?
Yeah, so here's something that I should have written down at any point and I didn't. So if you have the projection map from pi 1e to pi 1b, on homotopy groups, this is injective. So whenever you have a covering space, its fundamental group has to inject into the one downstairs. I guess that doesn't like contradict what you said though. But if you, okay, the other result that I have though, your fundamental group of your base downstairs has to act on the thing upstairs by deck transformations, right? So if your thing downstairs is trivial, that means the deck transformations of your covering space are also trivial. There's no non-trivial deck transformations. It's easy to see then that it has to only have one point in the fiber. Guess so.
Because if it's S2, then And in X-free and transitive, you can just move it to every point in S.
I guess so. Yeah. If you have 2 points in the fiber, you can connect them by a path,
Exactly.
and then you just project that down to S2, and that's already null homotopic. So those 2 points upstairs had to be the same point. Oh yeah, there you go. On the other hand, okay, well, anyway, here's the one I was thinking about just to move along. Remember this one? So R is certainly simply connected, and this maps to the circle, which is certainly not contracted. So this is a simply connected covering space. Therefore, the fundamental group of the circle is isomorphic to the deck transformations of the exponential map. So supposing we haven't ever thought about what is the fundamental group of the circle before, can we just compute this independently and then have a calculation for this? The answer is yes. Daniel thinks the answer is yes, and I'm going to say that it is correctly yes. Okay, so let's just start. This is probably going to end up having to be the last thing I'll talk about today, but it's so good. Okay, suppose, let's take a deck transformation. So f from R to R, continuous with the property that for all t, for all real numbers, we're supposed to find that the exponential map applied to t is equal to the exponential map applied to f of t. Right? This is what it means for f to be a map of covering spaces. It's fiber preserving. Just means that any t that maps to this value, f of t also has to map to that value. So let's suppose we have one of these. In other words, what can we read out right away? For all t, there's some n in z, such that, well, we know the periodicity of exp is 2 pi n. So f of t equals t plus 2 pi n. Right? Just for, in order for these to be the same, there has to be some n so that this is equal. And this n might depend in a weird way on t. And we have to rule out that possibility by using the fact that f is continuous. You might not necessarily get the same n for all t. You have to prove that you do. Yeah. Right? E to the it. What? Yeah. It's the same one that I used in the earlier example. Yeah, complex exponential. Oh, I even in my notes took 2e to the 2 pi it after being very insulting to physicists for doing that.
Oh, yeah.
So I'll keep it like this though. Okay, so now let's let f bar of t equal to f of t minus t. So whatever this is in 2 pi z. For each t, we get an element of 2 pi z. But if t is continuous, so f continuous, t is definitely continuous, so f bar is continuous. Right? And then since its range is discrete, it has to be the case that f bar is locally constant. It has to be constant on every connected component. And then since R is connected, it follows that f bar is constant. Isn't that crazy? That's a crazy proof. I thought that was such a crazy proof when I came up with it. So f of t, so there exists an n so that for all t, you get to switch those quantifiers. There exists an n in z so that for all t, f of t is actually just equal to t plus 2 pi n. It's just a shift function by this number n. So therefore, we started with an arbitrary element of the deck group, and we found out it's just exactly shifting by n. So we have a homomorphism z to the deck transformations of exp given by n goes to t maps to t plus 2 pi n Yeah, and this is, well, it's even a group isomorphism. It's a group isomorphism. So therefore, by our theorem, we've actually, this is a completely valid, and then some people really prefer this way of calculating that the fundamental group of the circle is the integers. So by setting up the theory of covering spaces and just doing this thing. It's actually way harder than the hands-on version. So there's like the elementary version where you like mark the north and south pole and you count how many times you cross. By the time you've proven that, you've essentially already proven the path lifting property for the exponential function. And by the time you show that it's like well defined up to homotopy, you've also proven like the homotopy lifting property for the exponential function. So it's sort of like the elementary hands-on proof that you'd probably see at a more introductory text turns out to be kind of equivalent to homotopy lifting anyway. It's kind of cool. So we got that. Okay. I shouldn't draw on for too much longer. I should maybe mention a couple other things and then just, yeah, okay, I've got 15 minutes, so I definitely can't like do any really big cool proofs. I'll mention another class of examples because you mentioned S2. This is a really useful class of examples. So, more example. If you have Sn and you have the action on it by plus or minus 1, this is a double cover of Rpn. Double cover. So the thing about double covers is you can always swap the 2 points and no one can stop you. That's always a perfectly valid deck transformation, and in fact, it's the only non-trivial deck transformation. Double covers always have the deck transformation is Z mod 2. So let's call this pi, I guess. So the deck group for pi is isomorphic to Z mod 2. And there, if, so Sn is simply connected if n is at least 2. And so what this is telling us is that the fundamental group of Rpn is Z mod 2. That's neat if n is at least 2. So it just kind of immediately tells us what is the fundamental group of projective spaces, just because we know that it's double covered by something that is simply connected. So it's kind of a freebie. Here about suppose that suppose E is actually contractible. Suppose you go all the way and it's not just simply connected, it's fully contractible. So then what is the point is that then B, which is really E modulo the action of pi 1b, right? This is an Eilenberg-MacLane space of type pi 1b in degree 1. So whenever you talk about Eilenberg-MacLane spaces in degree 1, you're essentially just talking about simply connected principal bundles over topological spaces, where the data in your topological space that you're interested in is just the fundamental group. So that's kind of like a, where do Eilenberg-MacLane spaces come from in degree 1? It's actually just simply connected covering spaces. Okay, and now I should probably wrap up with like the big important theorem that I'm not even going to start to prove. And I'm not sure if I'll have a follow-up talk, but I'm just going to let you know what you should be aiming for if you want to read more about this. Okay, so let's call definition. So if B admits a simply connected covering space, we call it universal because theorem, so if E over B is simply connected, and let's say E prime over B is connected, then there is a subgroup H is a subgroup of pi 1b. Maybe B should be path connected. But if the covering space is simply connected, then the base space has to be path connected as well, because it's the continuous image of a path connected space. Then there is a subgroup H with E prime is isomorphic as a covering space to E modulo the action of H. And the way this kind of works is you use your uniqueness of whatever maps, right? Since this is simply connected, its image in the fundamental group of B is trivial. That's contained inside every subgroup of B. So it doesn't matter what connected thing you have, right? You always get a map from your simply connected covering space to any other connected covering space. You just always do, just once you pick base points. And it turns out that you kind of figure out what should be the kernel of that map, and you turns out you find a bunch of loops and details that I didn't actually work out entirely. So this is actually part of something much, much more profound. And I'll just end with, this is the Galois correspondence. Oh, and I spelled it with an A over there. How do you spell correspondence? Is it an E or an A? Daniel's struggling. It is? It is E. Okay, and that one's wrong. That's okay. So let B be nice. And the words here are path connected. Is it path connected or is it connected? Locally path connected. I forget, there's three of them. One of them is definitely path connected, and another one is semi-locally, simply connected. If I had more time, I could expound exactly why we need to consider that. Let's say B be nice. If a space has to be nice in order to have a simply connected covering space. So we're supposing B is nice enough so that it has a simply connected covering space. Then, so we have isomorphism classes of connected covering spaces. So isomorphism classes of connected covering spaces over B is in bijective correspondence, but order reversing correspondence with conjugacy classes of subgroups of pi 1b. And what do I mean by like order reversing? I mean you have kind of the universal one upstairs at the top, PB, and then you do like, if you have an E here and an E prime in the middle, then what this is corresponding to is like you have a trivial group here, and then you have another group H, and then you have another group H prime. So that this E prime, the smaller one, is given by taking quotient by more stuff, right? And then down here you have B at the very bottom. No, that's not that. So this is B, and everything is considered inside of pi 1b. Right, so the base space B is what you get if you mod out by the entire pi 1b action, and everything in between happens by just modding out by smaller subgroups. And if your bundles sit in a row like this, then your subgroups also sit in a row. And if one bundle, intermediate bundle, is isomorphic to some other bundle, that means that whatever subgroup that you use to quotient out to get this one, for this one, this has to be in the same, what do you call it? Conjugacy class, where tilde means H tilde equals GH G inverse for some G in the fundamental group. So this is like, yeah. This is the big goal that everybody wants to make sure they get to by the time they reach the end of a unit on covering spaces. And there's like lots and lots of subtlety here in exactly like why exactly do we talk about conjugacy classes? And so that's something that I tried to figure out on my own, and I kept tripping over because it was like this morning and this afternoon. I didn't have enough time to prepare it by this talk. So yeah, I just want to end here. And I think I probably won't give a follow-up talk because like there's not too much else to say unless I give 20,000 examples or unless I want to just go over every single proof. But like this is the big thing. Thank you for coming to my talk on covering spaces. Questions? Classifying spaces of topological groups. What about them? BG. As a follow-up to covering spaces, talk about. I've already talked about classifying spaces. Yeah, but yeah. What else? So yeah, in this case, yeah, this is the classifying space for a discrete group. Yeah, so a lot of the stuff that you talk about in terms of classifying spaces and bundles and everything, the way to turn it into covering spaces is by forgetting topology and just taking discrete topology on all of your groups. And so yeah, there was another example was like if you take G as a Lie group, and then you take G delta as like the discretization. No. This is just a superscript. This is just a D that stands for discretization. This is G, the group, but it has the discrete topology on it. Yeah. And then you have that like maps from your space B into B of G delta, right? These correspond to homomorphisms from the fundamental group of B into G. Just plain group homomorphisms, don't care about topology. But like if B, but this is also supposed to be like, what is it? Flat connections or something? Principal G, yeah. So maps to G tilde are supposed to be like principal G bundles with flat connections. G delta. Because these are just given by like homomorphisms from the fundamental group. So they're determined by their holonomy. By picking an element G for each loop, you're getting the holonomy of some principal G bundle with connection, but really it's just maps to G, to BG with a discrete topology. So there's a Milner paper. He's like, what is it? He's like, bro, what is that map? No, which way does it go? So a discrete topology, every map out of a discrete topology is continuous. So he's like, you can go from B from the discrete topology on G to G by the identity map. This is continuous. And so you get a continuous function on classifying spaces. And he's like, what does that map do? It seems to be like a lift of this chooses a flat connection on your principal bundle. Right? So this maps to this is just boom, G principal bundle. But then this is G principal bundles with flat connection according to people that I don't understand because I don't know anything about connections. So lifting along this map is just going to be choosing a flat connection. I guess. Kind of cool, eh? So then if you take like the homotopy fiber of whatever this map is, then that space classifies flat connections or something on G principal bundles. Yeah, anyway, it's kind of cool. Well, this is yours. Don't want to steal that. Yeah, if I'd had more than 2 days, I would have had more coherent exposition, but I was actually proud of myself for how much I did. Yeah. Thank you. Yeah. Yeah, the big theorem about when does a space admit a simply connected covering space is also a really cool story. Yeah. It's you construct it out of the path space, but you take paths modulo homotopy relative endpoints, and you stick a really weird topology on it. It's not that weird. And then you just have to show it's simply connected and a covering space. But it's sort of technical and not intuitive. Yeah, I don't know. If I do a follow-up talk, I guess I would talk about that and prove this. But I probably won't. Fair enough. Fair